Greetings. We have our catch 22 Hartree-Fock problem, and we have made some progress in planning our strategy about how to solve this issue. So, our strategy is to minimize the expectation value of the Hamiltonian, which we wrote in terms of the 1 electron and the 2 electron integrals. The 2 electron integrals being the Coulomb and the exchange, subject to the variations in one orbital at a time, which is the frozen orbital approximation that we are referring to. Okay, all the other orbitals would not be varied, only one orbital at a time. Okay. So, subject to this, we seek that the expectation value of the Hamiltonian in the n electron Slater determinantal antisymmetrized wave function is an extremum. The constraints of course are that each 1 electron orbital remains normalized and orthogonal to every other. So, these are our constraints. Now, this is what our condition boils down to, that because of these constraints we incorporate these constraints via the method of variational multipliers, which is the Lagrange's method, and we introduced this method in the previous class, that the condition that a particular function is an extremum subject to certain constraints is completely equivalent to seeking the extremum of a different function in which the terms which go in the equations of constraints are multiplied by these parameters which are known as Lagrange's parameters or variational parameters, and accordingly we have these lambda I for each ith orbital. There are n of these corresponding to the normalization condition, and then there are these lambda ij and the lambda ji corresponding to the orthogonality constraints. Now, these parameters we also know something a little more about the Lagrange's multipliers. We know that if you write these variational multipliers as matrix elements like lambda 1 1, lambda 1 2, lambda 1 3 in the first row, and then lambda 2 1, lambda 2 2 in the second row, the matrix that you would generate, the n by n matrix lambda that you would generate, would be a Hermitian matrix. That is something that we have found out in our previous class. Now, if you look at the first term here alone, which is in this red loop over here, this is the sum of these single particle integrals and the 2 particle integrals, the Coulomb minus the exchange, right. So, I am now looking only at the variation in this expectation value of the Hamiltonian, which is made up of these 1 particle and 2 particle integrals, 1 center and 2 center integrals. We know that there are additional terms which will come from the Lagrange's multipliers, right. So, they will be plugged in later. So, at this point I am focusing attention only on the variation in the expectation value of the Hamiltonian alone, because they all come as additive terms as we have seen in the previous slide. So, I am now looking at only the first term, and the variation also in the kth orbital, just one orbital, we choose it to be any one of the n orbitals, let it be the kth orbital just for our referencing bookkeeping's purpose. Okay. So, it is only the kth orbital which will be varied, all other orbitals for I not equal to k will remain frozen. So, let us look at the first term in this. The first term is the single particle integrals, and you are seeking a variation in 1 electron orbital. So, these are the 1 electron orbitals, alpha I, you must sum over I going from 1 through n, and these 1 particle orbitals come here and here, and both of these are subject to the variation. So, essentially you will have, whenever this alpha I does not correspond to the kth orbital, that variation would vanish and the whole integral would vanish. The only term that will show up in your analysis is the one corresponding to the kth orbital. So, from the variation in this you will get delta u k star r, and then you have the rest of the term, right, from the first orbital. Then these dots represent all the other terms which include the 2 electron integrals. Okay. Likewise, there will be a variation over here, it is only the kth orbital. Okay. So, there will be additional terms over here, and you will then write all of these terms, keep track of each term. So, we will include all those terms, and I will show them on subsequent slides that we include these terms progressively. So, you keep track of the very first term that we are taking care of. Now, if you look at the variation in the kth orbital in the 2 center 2 electron integrals, this is in the Coulomb and this is in the exchange, and you have varied the kth orbital alone. Okay. You must sum over j, okay, but only the kth orbital is being varied. So, any variation in which you refer to a variation in any orbital other than the kth orbital, the corresponding 2 electron integral would vanish. So, that is not written over here because it goes to 0, and here you have only the variation in the kth orbital. This is in the Coulomb integral and this is in the exchange integral. Then you have additional terms which are complex conjugates, right. So, now you include all of them. So, this set has got the complex conjugation. So, here you had delta u k star r 1, here you have delta u k r 1 and so on, right. So, now we have got all the terms. Now, let us see if we can simplify this in some way. What is it that this leads us to? But we also have to include the terms coming from the constraints. So, some simplification is possible if you just examine this term. Now, look at this term. What do you know about the operator f? This is the single particle operator. It is a Hermitian operator. So, this is the term, and this being a Hermitian operator, this integral is completely equivalent to the integral which is written here at the bottom, from which the delta u k r 1 is a factor which had appeared in the earlier terms as well. So, you will then be able to combine all those terms. Let me go back one slide, because here you had delta u k star r, and then you had delta u k star r 1, delta u k star r 2 is here, this is delta u k r, but this is coming in the operand. If you put it behind the operator, then it could be extracted out as a factor, so that you can combine the terms, leading to some simplification. So, have a look at this, that we will use this relation, and now you have used it over here. This delta u k r 1 comes here, you have got the f operator operating on u k star r 1, and now you can look at all those terms which have got delta u k r 1. So, delta u k r 1 is common over here, you have delta u k r 1 over here, and then you have delta u k r 1 over here, and in all of these 3 terms it is only a multiplicative common factor in all the 3 integrands. So, you can combine the integrands. over here you have got delta uk star r1 and delta uk star r1 in these two integrands, and these come already, this one comes already before the operator. So, this operator is not going to affect this part. So, you can extract delta uk star r1 as common in this term and this term, you can factor it out. Now, can you pull it out of this term? What do we have here? The one with the kth label is delta uk star, but the argument is r2 rather than r1. So, you cannot extract it straight away, right. But then both r1 and r2 get integrated out, right. This is the double integral over dv1 and dv2, both r1 and r2 get integrated out. These are dummy labels. So, you can write x in place of r1 and y with in place of r2, or you can write r2 in place of r1 and r2, you can just interchange r1 and r2 labels, they are dummy labels which get summed over. Okay. Integration is just a sum and they get summed over. So, if you just exchange the dummy labels r1 and r2, you can extract delta uk star r1 from this term as well. Can you see that? And then you can combine all of these three terms. Likewise, you can combine all of these three terms in which you can extract delta uk r1 from here, delta uk r1 from here, and delta uk r1 from here. From these three terms you can extract delta uk r1, and then you can write these terms exactly by factoring out by common terms, and they get a very simple form, because now you have a fairly complicated set of terms, but of course we still have to include the terms coming from the constraints. So, we will do that later. So, here you have factored out this delta uk star r1, factored out the integration over the element v1. Okay. This is a triple integral, mind you. What happened to the summation over the spin variables? That has already been carried out, and that gave us the Kronecker deltas, and all that process has already been achieved, it has already been completed. So, now you have integration over v1, then you factor out the delta uk star r1, and then all the terms involving integration over r2 are in the Coulomb and the exchange terms, and you have got the complex conjugate of what is in this bracket over here. So, here this is integration over v1, the one factor which is common extracted is delta uk star r1, and the factor which is extracted over here is delta uk r1, and this multiplies the complex conjugate. So, these two terms in the top row and in the bottom row, which are added to each other, are completely equivalent, they are just complex conjugates of each other. Okay. Now, let us include the terms coming from the constraints. So, you have got these terms coming from the constraints, this is coming from the normalization constraint, this is coming from the orthogonality of I with j, and this one from j with I. Okay, these are complex functions, and the real part and the imaginary part can be varied independently. So, you have the lambda matrix generated, which is a Hermitian matrix, and just for brevity I have now written this expectation value of the Hamiltonian as in this notation, which is completely equivalent to this. Okay. The rest of the terms are written as they are, and this is what we have. We have got the variation in the expectation value of the Hamiltonian, which is the average value, and then to this you must add the variation in the terms coming from the constraints, and there are the normalization constraints and the orthogonality constraints. We also know that all orbitals other than the kth orbital are not changed. So, this is our constraint. So, here you are varying all of these ith orbitals, but any variation in I not equal to k would vanish. Therefore, the terms which you must include are only those for which I is equal to k. So, here you have got the delta uk star r1 uk, right. Whenever I is not equal to k, that term would vanish. So, out of these n terms you have only one corresponding to the kth term, which is allowed to be varied under the frozen orbital approximation. All the other n minus 1 orbitals are frozen, and therefore, variations in those n minus 1 orbital would vanish. Okay. So, this is coming from the variation of delta uk star r1, and this is coming from the variation in delta uk, which is the complex conjugate. So, there are two terms coming from here from the variation of this. This is the product of two functions, right, and you must seek variation in both. Then from the Coulomb and the exchange terms, likewise you have only the variations in the kth orbital. So, delta uk star r1, and then over here you have got the delta uk r1. This is coming from the orthogonality constraint. Okay. So, this is coming from the normalization constraint, this is coming from the orthogonality constraint, and the variations in the single particle, the 1 electron integrals and the 2 electron integrals, those are already sitting over here. So, now you have to write all of these terms together. Now, notice that if you look at these terms, this is a variation in the kth orbital, and in the Dirac notation or in the vector notation, this is completely like the inner product of a unit vector on its change. Delta uk star is a variation, right, and any variation has to be orthogonal to the original orbital, otherwise it is not a variation at all. Okay. For delta uk to be a variation, it has to be orthogonal to the original orbital. If it has any component along the original orbital, it would not even mean a variation, and we know it from our ordinary vector algebra. If you take spherical polar coordinates or cylindrical polar coordinates or any coordinate system, you have got these unit vectors which change, right, from point to point. You know that the change in any unit vector delta u is always orthogonal to the original vector. So, it is the same idea over here, and these two terms which represent the norm or the inner product of a base function with its change, this integral would vanish in both of these terms. Easy, but very useful. So, that simplifies the number of terms that we are working with, and now we can eliminate these two terms and write our condition as the variation in the expectation value of the Hamiltonian, and now you have to worry only about the terms coming from the orthogonality constraints and not from the terms corresponding from the normalization constraint. So, that makes our relationship rather simple to be analyzed. So, let us have a further look at the consequence. We have now combined all those terms. So, these are the basic terms that we work with. So, here you have got the terms corresponding from the orthogonality constraint, and these are the terms coming from the seeking the extremum of the expectation value of the Hamiltonian itself. Now, everything is here. Okay. Do you see all the terms? You have got the 1 electron integrals, the 2 electron integrals, and then you have got the constraints. everything is put in. So, let us factor out these terms, and now you have two rather interesting integrals to look at. What is this? This is an integration over the coordinate 1. This is an arbitrary variation in the kth orbital. So, look at this as an integral of an integrand, the integrand being a product of two factors, one is this factor and this is the other factor. This is an integration over coordinate 1, integration of what? Integration of an integrand, that integrand is a function of R1, and that function of R1 is written as a product of two factors, one is this, which is in this beautiful bracket. This is an arbitrary variation in the kth orbital. The other factor is what is sitting in this bigger bracket from here to here. This is the other factor. This is also a function of R1, because in this the integration over R2 is carried out. So, 2 is a dummy label. Once that integration is carried out, you are left only with a function of R1, and you have a similar exercise over here, that you operate on UKR1 by this one electron operator, and then you are left with some function of R1. So, essentially you are integrating an integrand which is written as a product of two factors, one of which is an arbitrary variation in delta U, which means that the other factor must vanish. Okay, there is no way this integral would vanish, because when you integrate over R1 the left hand side is 0, right. So, you must get 0 from this integration, and the only way you can get it is if the other factor is necessarily 0. There is no choice, and this is an important conclusion that you can derive at, and this is at the very heart of the Hartree-Fock formalism, that our process of seeking an extremum of the n electron Hamiltonian in an antisymmetrized n electron wave function, which is the Slater determinant, this expectation value would be an extremum subject to the constraints of normalization and orthogonality if and only if this other factor in the integrand vanishes, because this factor is multiplied by an arbitrary variation. No matter what this variation is, this integral must vanish. Okay, so, independent of this factor, you have got a product of two factors whose integral vanishes, mindless of the fact what one factor is, then the other factor has to be 0. So, what is inside this red loop must necessarily vanish. Now, this is a conclusion that you can draw from our analysis, the one which is complex conjugate, right. So, that will be the other box which will have to be 0. Okay. So, this factor in this red loop must be 0, and what is over here from the other term, as you are pointing out, this would also be 0, which is just the complex conjugate of this. So, you have got a complex number which must be identically 0. So, it is not surprising that its complex conjugate should also be 0, and that comes automatically from this analysis. Okay. We have already seen that these are complex conjugates of each other. So, both are true, and you can work with either. So, this is our conclusion, that what is in this red loop or its complex conjugate must vanish, and let us write this condition which is subject to the approximation we have employed, which is a single particle approximation. So, remember that we have made a certain approximation in our analysis. This approximation is not completely physically realistic, because you know that when you vary an orbital, you are changing the probability amplitude and therefore the probability density, therefore the charge density, and any change in the charge density will generate fluctuations in the electron density around it. Okay. So, it is a certain approximation, and within the applicability of the frozen orbital approximation, we know that what is inside this red loop must vanish. There is a term corresponding to the complex conjugate which must also vanish, right. The corresponding complex conjugate term would also vanish, and if this is equal to 0, I take this term to the right side with a negative sign. That is what I have done in the next slide. So, the term involving the variational multipliers is this one. Okay. This is the term which goes to the other side of the equation sign with a minus sign. So, that is what is coming on the right hand side. The left hand side is the remaining terms except for that involving the Lagrange's multipliers. This is the Hartree-Fock equation. Okay, this equation that you are looking at is what is called as the Hartree-Fock equation. What is it? Actually, there will be n such equations, okay, because we have written this only for the kth orbital, but k is any index from 1 through n. So, there will be an equivalent expression for all the remaining n minus 1 terms also. Now, this is a set of n coupled integral differential equations. Why coupled? Because here you have ukr1, but here in this integrand you also have the ujr2, and these get summed over j going from 1 through n, right. So, all the other orbitals are also included there in some sense. So, these are coupled equations. They are integral differential equations. You can see the integration which is involved. There is differentiation is also involved because the operator f includes the kinetic energy term, right, which has got the differential operator. So, these are coupled integral differential equations, and you can solve them iteratively using numerical methods. So, the Hartree-Fock equations are coupled, n coupled, it is a family of, or it is a set of n coupled integral differential equations. What do they tell us? They represent the condition that the expectation value of the Hamiltonian is an extremum subject to the constraints of normalization of each single particle orbital and the orthogonality of these orbitals with each other, within of course the applicability of the single particle approximation, the frozen orbital approximation, that all the other orbitals are not varied at a time. So, the Hartree-Fock equation emerges as a condition to be satisfied, that this condition must be satisfied. If this condition is satisfied, it is a necessary and a sufficient condition. If this condition is satisfied, you would have achieved your goal. What was your goal? That the expectation value of the Hamiltonian must be an extremum, and that the variations must preserve the normalization and the orthogonality of the single particle orbitals. So, subject to those constraints, that the average value of the Hamiltonian must be an extremum was our goal, and this goal would be achieved if this condition is satisfied, which is what we call as the Hartree-Fock equation. Now, we can simplify this further, because we do know that lambda, these variational multipliers, are, they make up a matrix n by n matrix, which is a Hermitian matrix, because lambda kj must be equal to lambda jk star, right, and therefore this is a Hermitian matrix, and if it is a Hermitian matrix, you can find a unitary transformation which diagonalizes it. So, you can look for a unitary transformation which will diagonalize the matrix of the variational multipliers. That will simplify things further, because in the matrix lambda you have got n square terms, right, and out of these n square terms you really need only n terms, because if you carry out a diagonalization of lambda, you will have non-zero elements only along the diagonal, one in each row or each column, and then when you sum over j on this lambda k j, there will be a Kronecker delta, and that will simplify this very significantly. So, now we seek a diagonalization of the matrix lambda through a unitary transformation. This unitary transformation is C. So, C dagger lambda C will give you a diagonal matrix. Okay. C dagger lambda C is a diagonalization process which will give you a diagonal matrix, so that the diagonal elements will have a Kronecker delta, right. And the diagonalization, what is relevant to this diagonalization are, remember that the orthogonality of the spin part is already taken care of. So, the indices of C, the I and j indices of C will have nothing to do with the spin variable. So, implicit to this Cij is a Kronecker delta which guarantees the orthogonality of MSI and MSJ. So, it will be orthogonality with respect to other indices, because that is already taken care of. You are now varying the space part of the orbitals. Okay. So, far as the spin part is concerned, you already know that the down spin is orthogonal to the up spin. So, there is nothing to vary there. There are only two states. We also know that this is a unitary transformation. So, C dagger is equal to C inverse, and we can now use this to write this in terms of the basis in which lambda is diagonal. Our original Hartree-Fock equation, which is here at the top, which emerged as a necessary and sufficient condition that our expectation value is an extremum subject to the constraints we refer to. This original expression, Hartree-Fock equation, is in a basis in which lambda was not diagonal. We can now write it in a basis in which lambda is diagonal, and this basis is obtained by operating on this unprimed basis by this diagonalizing matrix C, which is C dagger here. So, C dagger u will give you the u prime wave functions, right, and you can write this in the long form if you like, that every prime function can be obtained as a linear superposition of the unprimed base functions, because this will give you a certain basis set. You can always do a linear superposition of these base functions to give you new base functions, and this is the unitary transformation which will preserve the norms and orthogonality, right. So, you have the inverse transformations also. So, every UKR1 over here can be replaced by this summation, and then you will rewrite the Hartree-Fock equation in terms of the primed functions instead of the unprimed functions. So, the Hartree-Fock equation, which appeared as a condition, can be rewritten in terms of functions in which the matrix of the variational multipliers is diagonal. So, I will let you work that out as an exercise. Replace each of these unprimed functions by the corresponding primed functions using this inverse transformation, right. Rewrite the Hartree-Fock equation. What will it give you? It will give you an equation in just the primed orbitals and not the unprimed orbitals. Okay. But the primed orbitals are also orthonormal, because you have carried out just a unitary transformation, and using the properties of orthonormal functions you will be able to reduce those multiple sums using the Kronecker deltas, and you get an equation which will preserve the form. You get an equation in the same form, except that it is now in the primed orbitals. You get an equation which is completely identical to the previous one, except for the fact that it is now in terms of the primed orbitals, in which lambda is diagonal. And now why do you need the primes? You need the primes only if you want to distinguish from the unprimed, and in this equation everything has got a prime on it, so you might as well drop it for simplicity. Okay, and having dropped these primes, you have this equation, but this is not the original one that we got, mind you. It has the same form because it has been obtained through a unitary transformation which preserves the form of the expression, but it is now in a form in which the lambda matrix is diagonal. So these are called as Hartree-Fock equations in the diagonal form. Sometimes these are also called as Hartree-Fock Dirac, because if the 1 electron orbitals are not just the spin orbitals, the 2 component spin orbitals, but if these are the 4 components Dirac orbitals, you can do this entire analysis in exactly the same way and extend this whole formalism from the non-relativistic Hartree-Fock to the relativistic Hartree-Fock, which will make it the Hartree-Fock Dirac formalism. Okay. So in one go we do the Hartree's method, which is a subset of the Hartree-Fock, and we also do the Hartree-Fock Dirac, or which is the relativistic self consistent field, okay, which is called as Hartree-Fock Dirac, or sometimes it is very often referred only as Dirac-Fock, but that will be injustice to Hartree, who really set up the whole procedure. So this is called as Hartree-Fock Dirac. Now we know that these are the diagonal elements, okay. So the subscripts I and j are equal, the row index and the column index both are I for lambda, right. So you have got a lambda I on the right hand side, and since only one index is required because the row index and the column index is the same, you might as well use only one index, and we introduce an epsilon I which is minus of lambda I. So now you have an equation which looks to some extent like an eigenvalue equation, if you see it that way. Not quite, but it is beginning to look like an eigenvalue equation. But you have to be careful, because just because it looks like an eigenvalue equation does not mean that it is an eigenvalue equation, but at least it has got some similarity, right. And by introducing this epsilon I, you write it in a certain simple form. What is this epsilon I? It is the Lagrange multiplier lambda I. It is not the original Lagrange multiplier that we began with, but it is the one that you get when you diagonalize the original matrix of lambda multipliers through a unitary transformation. Okay. So this is the Hartree-Fock equation in the diagonal form, in which epsilon I takes place of what an eigenvalue does in an eigenvalue equation, if this were an eigenvalue equation, which let us not assume that it is just because it looks like it, okay, but it has got some similarity with that. And this is what we recognize as the condition, as the necessary and sufficient condition that must be satisfied. Now we are going to raise these two questions. One is, what is the connection with observables, because after all the whole idea of developing a theory is to connect it to experiments, to observations. That is what physics is about. Okay. So we have done some mathematics. the mathematics that we have done is very elementary. All we have done is variational calculus. We have just stated that okay, if you have got a function of a certain variable and if this variable has an extremum, then the point at which it is an extremum should be such that the tangent to that curve will have 0 slope, right. That is all we have done, except for the fact that we have extended this idea to a function of many variables, right. We are aware that there are certain issues that remain to be addressed, such as whether this extremum is a maximum or a minimum or a saddle point, and that point we are yet to discuss, we will. But subject to this, we have found a way out of the catch-22, that the solutions that we are looking for, which we did not know how to extract, will result from numerical iterative solutions to the n coupled integral differential equations. If we seek iterative numerical solutions, if we get solutions in this form, and then the question that remains to be answered, and this there are two questions actually, many but two important questions. The two important questions are, what is the connection of all this with observations, because that is what physics is about, and that is the question I will take up in the next class. The other question I will take up in the next class, if this is really an eigenvalue equation, okay, it just looks like it, is it really an eigenvalue equation, okay. So we will take up these questions in the next class, and of course we have to discuss many other aspects of the Hartree-Fock formalism about whether it is an extremum, a minimum, a maximum, a saddle point, okay. All we know is that it is a stationary point, that it is an extremum, we do not know. And then there are other issues like the frozen consequences and the implications of the frozen orbital approximation, how good is it and what are its limitations, okay. So these are some of the questions that we will take up for our discussion in the next class. Any question for today?
So we subjected to condition for extremum.
Yes.
And our objective was to find out the wave function,
correct,
which will be minimum, but we result with a condition,
yes,
which are in the form of some integral differential in matrix form.
correct.
So how could we extract the wave function which will be minimum, which will give my
So you have got n coupled integral differential equations, right. You kickstart the process by some trial functions, okay, and then solve them iteratively till you get self consistency. You understand what is meant by self consistency. Now this was the original idea that we discussed in the context of solving the catch-22 problem, that your Hartree-Fock equation H psi equal to E psi, where H and psi are respectively the n electron Hamiltonian and the wave function, okay. Normally if this was just a single particle problem, you get the psi by solving the differential equation. H psi equal to E psi is the differential equation, you know how to solve a differential equation subject to boundary conditions, you get the solution and the problem is done, right. In the many electron problem, the operator H requires the solutions. You cannot set up the operator unless you know what the solution is. So that was the catch-22, okay. Now what we have found out is that this catch-22 is completely equivalent to solving these n coupled integral differential equations, because what has come out as an equivalent criterion, that the solution should be such that the n electron Hamiltonian must have an extremum for its expectation value subject to constraints. That condition is represented by the Hartree-Fock equation. This is the condition. Okay, it is a condition. So, Hartree-Fock equation is essentially a condition, it must be fulfilled. It is a necessary and sufficient condition. Condition for what? That the variation in this expectation value of the Hamiltonian is 0, subject to the constraints of normalization and orthogonality within the frozen orbital approximation. So, there will be certain limitations. Okay. So, we can and we will discuss the scope and the limitations of this frozen orbital approximation. We shall do it in the next class, but essentially we have got a necessary and sufficient condition which is completely equivalent to the statement of the problem itself. So, we have restated the problem in a different form, but the original form h psi equal to E psi did not give us a start as to how are we going to solve this problem. Now, we have a start because the same problem has been posed in an alternative and equivalent fashion. What is this alternative form? That the n coupled integral differential equations must be satisfied self consistently. If you solve one of them, it is not enough. The solution to one will disturb the other n minus 1 equations. Why will it do so? Because they are coupled integral differential equations. Okay. So, you take one, solve it, but in such a manner that there is self consistency, that solution to any one will not disturb the solution to the other. And how would you evaluate this? By setting up some convergence criterion. When you say that it should not disturb the other orbitals, what it means is that okay, if the other orbitals are to turn out to be different from the original ones that you started out with, then let the change between the previous step and the next step not be any more than some delta. You can set that to be like 10 to the minus 4 in some units, or 10 to the minus 6, or 10 to the minus 8, that will be the convergence criterion, right. That is a numerical criterion that you will impose, and subject to that criterion you will seek self consistency. I will like to mention that at the end of our treatment of the Hartree-Fock formalism many years ago, this was very many years ago in a class of this kind, one student got interested and she said that okay, how do I set up the Hartree-Fock equation? I want to do it and solve it numerically. So, she wrote a program and got self consistent field solutions. This was a student in a class exactly like this. So, each one of you is capable of doing it. She has done it. This was a part of her MSc dissertation and we have a copy in the lab. So, you are quite welcome to see that report, and you want to try it out, welcome. So, let it be known that it is something which students at your level in this very classroom actually do it. So, thank you all for today. If there is any further question, I will be happy to take, otherwise we proceed from this point in our next class.